Now we have the idea of the structure and the behavior of a neural network. A neural network can be thought of completely specified by the collection of all the weights between layers. Sometimes they are called coefficients. As the structure of the neural network has been determined, the number of the weights the neural network contains is fixed, and that is the design stage of the model, or we can call that model selection. After we have determined the structure of the model or the neural network, the next job is to, when given the training data, we need to pick up the specific model in the entire family of the model with the same structure that fit the data best. To achieve this goal, we need a concept called loss. We have already encountered the loss in the previous week's study of perception and also in the introductory data analytics. A loss is actually a heavily loaded concept because it collects all the information in the training data in one real number. That is the measure of how the data model match the observation of the real data. For example, if the target is for us to use a neural network to mimic the output of some process, given the input and the output is to be a real number, we can use the squared error between the output of the neural network model and the desired output. That is called regression problems. And in the example we have just seen, that is a classification problem. As we discussed in the beginning of this introduction, internally, neural network can represent the classification problems using the same number of output neurons as the number of classes to be predicted. And in each of the output, remember that we can render the output activation of each neuron between 0 and 1, and we can consider that quantity to be the probability of the model from the model's perspective that the input sample belongs to a particular class. In that case, we can calculate the probability of the desired class according to the model. If the model thinks the input sample belongs to the target class with high probability, we say that this model incurs a small loss. Otherwise, if the model will output some very small probability to the target class, that translates in everyday language is that your data model thinks it is impossible for the input data sample to belong to the class which it is actually is. This hypothetical impossibility by the model should give the model a higher loss. So there are different ways of design losses which you can find in many good references, and in the end of this class I will provide some good book on this topic. Anyway, after determining a loss, we will have the very condensed representation of the matchness between the data and the model and the data. So now to fix the model becomes the behavior becomes the process of minimize. Normally we call it optimize the loss. Remember, we just talked that a model will be determined by a certain number of coefficients or weights. So a model can be thought of some object living in a high-dimensional space. For example, if you have 4 coefficients, the model will be an object of 4-dimensional, a point in a 4-dimensional space. Because if you pick up arbitrary 4 numbers, you will determine a particular neural network model in that fixed model family. Okay, and after we have the loss join this process, we will have 4 plus 1 numbers in this entire operation. The 4 numbers represent a model, and the 1 number represents how well that particular model fit to your data. Okay, and remember that the 1 number of loss is fixed for all kinds of models. You need 1 particular number to measure the matchness. And the 4 numbers is just for this example. You can have models of 40 numbers, 400 numbers, or even more. Okay, whatever numbers you have n numbers of coefficients always to fix the model. And now the process of training the model or fit the model to the data becomes a game in this n plus 1 or 4 plus 1 space. In this space, you have the freedom to move the model in the n, or in our example, 4-dimensional space. And after each of your movement, you will receive a loss, and the objective is to minimize that loss. That is called training or optimization of the model. The algorithm of minimizing the loss is intuitive. In the weight space, in the above-mentioned example, that is the 4-dimensional space, we can calculate a direction. Along that direction, if we forward a certain time step, the loss will reduce most. Sorry, the loss will reduce most along 1 direction. However, the principle is easy to see than to do, of course. In practice, there are a lot of challenges regarding to the training, regarding to the optimization. Firstly, in the very first, one has to be able to compute the direction. We need to know along which direction we travel, the loss will reduce mostly. The way to calculate that direction is called to find the gradient of the loss with respect to all the weights. That task is theoretically trivial because we know the function relationship between how a neural network transforms the input to the output, but practically challenging because the transformation has been done in many steps. So if we apply the chain rule of calculating the derivative of a function with respect to its arguments or its inputs, the calculation will be prohibitively expensive to do on digital computer. A very clever way to calculate the gradient has been invented, or maybe several decades ago. That is to apply the chain rule in a dynamic programming way. The algorithm is called backpropagation. The general idea is to calculate quantity called error signals for each layer of neurons. From the very last layer, that is the loss, the computation where we find the loss, and the computation is to try to figure out if I want the loss to be to reduce, how should I adjust the input to the calculation of the loss. And this adjustment is called the error signals to the last output layer of the neural network. And then we backpropagate this error signal to one layer before. The principle of the calculation is to design how should I change the output of the second last layer so that the output of the last layer will change with respect to the error signal I have just calculated. This desired change becomes the error signal of the second last layer of the neurons. Then we do the same calculation and backpropagate the error signal for the second last layer to the third last layer, so on and so forth, until we reach the input and the very first layer of the neural network. Of course, we cannot change the input because that is the data and is given. Along the way, we can formulate at which direction we would like the width to change at each layer of the neural network. And then the optimization becomes trivial. We just need to travel along the direction a little bit to see how it affects the loss. I would recommend some dedicated video lectures on backpropagation, especially the hinting ones. Actually, the hinting course is the entire course about all aspects of neural networks. And there are a few short videos, particularly about the backpropagation algorithm. But remember that if the concept still has give you some confusion in most practical applications, you do not need to implement those algorithms, the backpropagation algorithm yourself.